So we're going to discuss discontinuities and the graphs of piecewise functions a little bit more, which I know some of you are scared about. But what we're looking at is that we have three scenarios. And one scenario is that wherever you have your bounds of your pieces, we're just drawing the graph by the way, maybe you have like an absolute value function. And let's say you have a connect at a closed circle connected to, I don't know, a parabola. So it looks something like this. That would be a goofy looking thing. But what we're talking about is that our pieces are connected at a closed circle. So maybe I'll draw the same thing over here, except the piecewise is connected at an open circle. Something like that. I'm just making this up as I go, by the way. But then we have a third situation which the pieces do not connect at all. So maybe, I have the same absolute value function with an open or a closed circle. And then maybe down here is where my parabola is located. And we're going to talk about what we're going to call these. And one of the names is actually called a jump discontinuity, which you can definitely see it's almost like you're right here and then you jump to the next one. But anyway, by the way, one of these does not need, both could be open, one could be open, but they both cannot be closed. And think about, well, what would it fail if they were both closed dots? Well, it would fail the vertical line test. By the way, this example, for the record, could have a defined value somewhere else. But now we're getting into kind of tricky math, so instead of confusing you with that, I'm just going to leave that as is. Okay, so what we have is, first of all, we call these two scenarios over here, these two, discontinuous functions, or they're not continuous. And there's a pretty lame explanation out there for what it means to be continuous. The lame explanation of continuity is that once you put your pencil to the paper or my pen to the board, I never pick my pencil up going from one to the next. So this is an example of a continuous function because I never pick my pencil up off of the piece of paper. Now this, even though they look like they're connected, that's an important thing. When you're drawing it though, technically you have to lift your pencil off the board and then put it back down to the right. Now we draw this circle here to show that it's undefined. So this is discontinuous, and this one's definitely discontinuous because once you get here you have to pick your pencil up off the board to go to the right. So both of these are discontinuous, or you can just say not continuous. You need to understand the word though. So we are looking at the values for x that are just to the left of 0 and to the right of 0, and we're examining these values because that's where the piecewise function is split up. So to the left of 0 is using the less than sign. It's going to be your directions for the top equation. And then to the right, we're going to use the bottom equation, which is this. So if I were doing the problem, I would graph the piecewise function first, where we have shifted left 3, up 4. It's a parabola, but it's reflected, so it's a downwards parabola, so it goes down by 1. And then the next time it goes down by 3. Down by 3. Now, notice that it stops at x equals -5, so I actually stop the left side of the parabola, and it is equal to, so I'm fine to put a closed circle there. But I need to go all the way until I get x equals 0, which is, so down by 1, down by 3, the next one's down by 5. And it's an open circle right there. Let's make that a little bit larger of an open circle. Is our parabola there. So now I would go to the right side and graph the absolute value shifted to right 2, down 7. 7. Absolute value is this V shape, and it equals at 0. So now I can actually fill in that circle, and it goes infinitely to the right, so I can stop at some point, put an arrowhead there. So is q of x defined in the problem? That answer quickly is just yes. It's just saying, so we're looking at these x equals zeros. Now, which equation is it defined for? It's the bottom one because it says equal to. So that's your clue to go to the bottom equation and plug in 0 for these x's. 0 minus 2 is negative 2. Absolute value is positive 2. Minus 7 is negative 5. So q of 0 is actually equal to negative 5 from the bottom equation. And now what we have is new notation for you. So be familiar with this because we're going to say this a lot. As x approaches 0 from the left, that's what that superscript minus sign means. And I'm writing in orange for a reason, because it is on the left side of x equals 0. Well, which function was on the left side of x equals 0 is the orange equation. And you can tell because it's a less than symbol, it's telling you to go to this problem. Now, if you look at the graph, you can tell that the y value that it's getting closer and closer to is negative 5. Now, I know it's undefined, so you're not technically plugging in 0, but you are, if that makes sense. And that's actually the next question down here. Because x could have been negative 0.00001, well, if you plug that in, you'll get negative 4.99999, but it's getting closer and closer. That's why we have the phrase approaches with this arrow. Which brings me to the next one, is all the same words as x approaches 0 from the right, so ... from the right. That's what that superscript plus sign means. And this one, I think it's also pretty obvious that it's negative 5. And as we look at this picture, you can see, like, it's actually defined at x equals 0, but if it wasn't, you could still say x equals negative 5, or sorry, y equals negative 5 there. Now, so instead of working through this, I kind of explained, I'm going to share the answer key with you. So if you want to hit pause once it's shared, here you go, share it with you. You can hit pause and copy that down, fully understand it, and notice that they use the top equation for the left side, plugging in 0 for x to get that value, and 0 from the right side is using the bottom equation to get that. Okay, so I can mess up. There we go. Go back and explain the next section. Okay, maybe I should spend just a tad bit longer. What we're looking for is this is an example of a continuous function. If you look at the graph, it's pretty evident that that's continuous. And what is unique about this problem that makes it continuous is the function is defined and has a numerical value. That numerical value matches this value and this value. So really what we're looking for is 1, 2, 3 things, and all 3 equal the same value. So it'll make more sense when I get to the next thing. There's 2 different types of discontinuities. There's what, we'll just keep it simple for right now. There's jump discontinuities, which I mentioned before, and there are holes. And sometimes we call the holes point discontinuities. When we get to calculus, just for the sake of learning some fancy terms, sometimes we call these non-removable. We don't need to know these yet, and if we do, I will remind you on which one's which. Non-removable and removable discontinuities. Just different math people. Different math people use different words, so be ready for either. The quick explanation is, like, if you look at a graph if there's a jump in the problem, then it's going to be a jump discontinuity. So the F and G have two examples of jump discontinuities. And then here's two examples of holes in the graph, but they're connected on the same side. Now I know some people look at this and they think that's a jump, but because the left and the right side are approaching the same value, we're going to call them holes or point discontinuities. I forget which one they use in the homework, so I want to point out both of those, I guess. So I'm going to have to flip back and forth. I apologize if that makes you dizzy. But if you look at F, definitely has a jump because you can see it. Now down the road, you're not going to be able to see every graph. So as you look at it, so let me go back to F, is the function defined? Definitely not. If we're looking at x equals 3, and I guess I should clarify, we're looking at x equals 3 because that's where one piece stops and the other one begins. So at x equals 3, it is not defined. So again, if anybody's confused, there's no equal to, and if you look at the graph, both of them are undefined. So we're just stopping just shy of x equals 3, and then the second piece begins to the right of x equals 3. And so as x approaches 3 from the left, if we're looking at the graph, on the left side of x equals 3, we're getting closer and closer to 2. And on the right side of x equals 3, we're getting closer and closer to 4. So the left side, I hope I'm clear that I'm talking about the y value. And on the right side, the y value is 4. So on the left side, it's 2, and on the right side, it's 4. So what you need to notice is, so this was like number 1 on my list I made earlier. This is number 2, and this is the third piece. That since these are definitely not the same numbers, there's not even a number up here, it's discontinuous. Now, what makes this a jump discontinuity is that this number does not equal this number. And you can numerically figure it out by doing the work that they showed. As x approaches 3 on the left, we're doing the function f of x for the top equation. So the top equation is 3 plus 3. Let me write out the work. Whoops, I went the wrong way. And then minus 4. So 3 plus 3 is 6, minus 4 is 2. You see how the numbers match up. I hope you're picking up on everything. And our actual work as x approaches 3 on the right, and that function, we're going to use the bottom equation. So as I go back, the bottom equation is negative 1/3 x plus 3 plus 5. The x value being 3 plus 5. Well, negative 1/3 of 3 is negative 1 plus 5 is 4. And again, I hope you're recognizing how you can do this without looking at a graph. And let me sum up things, and I'm at my time limit. And so I'll have to pause the video, or stop the video and do another one. Since 2 does not equal 4, f of x as a jump discontinuity at x equals 3. So again, pause the video, re-examine everything, and we'll move forward with the rest of these notes.